So hi everyone, I'm Ufuk. I'm also a committer in the Flink project, and I would like to talk to you about unified batch and stream processing in Apache Flink. This will be a high-level overview of Flink's new runtime. So starting this talk, batch processing has kind of dominated this big data space from the beginning, most prominently with the Hadoop system, which is a batch processor, and which allows you very nicely to program your applications with high latency. It usually works on static files, which is one of the reasons you get this high latency. But what's happening recently is that people are kind of transitioning away from like batch processing systems to stream processing systems. And in contrast to this high latency, which you have with batch processing systems, you try to reduce this latency and work with infinite event streams. So the question for today is, how does this look from a high level point of view? So, and from the runtime perspective, the question is, what's the real difference here from the runtime? So is there any? So what's happening for batch processing systems, the infamous word count example, you want to count your words for some weird reason, is you have your data stored most prominently in HDFS as static files. You parse the complete file as input, you do some processing on it, and usually for most systems write out this intermediate result completely to a file, do some further processing, and then write out the complete result. So, and this is actually also where the latency comes from. You work on like whole static files, usually materialize the intermediate results, and then write out whole files again. So what's different for like stream processing systems on a high level? For one thing, you usually bring up your whole program at once, and then work with incremental updates. So you read incremental updates, keep the data moving. You usually don't want to write it out to disk, and write out incremental updates again. So this is a very simplified view. There's a whole lot of things happening on the higher layers, like Windows, etc. But from a runtime perspective, I would say this is more or less accurate. So the question is actually, do you really need separate systems for this kind of processing? So do you really need a different system to do this batch kind of processing and do this stream kind of processing? For Flink, the answer is no. If you are familiar with Flink, have used it, you will know the dataset API, which is essentially the API for batch processing, and the newly introduced data stream API for stream processing. And the thing to highlight here is that both run over the same runtime. So there's one runtime which supports different kinds of processing. So as an introduction to this runtime, I want to present you the two building blocks of the runtime, which are like the operators and intermediate results. Operators represent computations, some kind of arbitrary computations over your data. And most of you will be familiar with the operators available, most prominently map and reduce. And Flink also has some internal operators for doing the heavy lifting like sorting and hashing. And what you can do with these operators is combine them in a more or less arbitrary way and express your problem. So this is, any questions to this point? So this is like half of the story, and the other half of the story are these intermediate results, which have been introduced to the runtime, I would say, end of last year. And they are a logical handle to the data produced by these operators. So if we go back to this picture, you see here that the operators produce results, and these are now a first-class citizen in Flink. So what this means, I'll tell you in a minute. So, for example, if you write your WordCamp program, on the left, this is the dataset API and the Java example. This will be translated to a data flow, which is here on the right, with a map operator producing some intermediate result and the reduce operator. And the intermediate result is logical in the sense that it doesn't, at this point, you don't need to specify how this intermediate result is implemented. So it can have multiple implementations. And what I want to talk about today are like different characteristics we have implemented so far for these intermediate results. So the first thing is, the first question these intermediate results can answer is how and when to do the data exchange between operators. So we call this pipelined versus blocking intermediate results. So as an example, you have your map reduce job and you are doing a blocking data exchange. So what happens is you consume your data in the map operator, do some transformations on it, and you produce part of your result. This goes on, and after that, after you have completely produced your result, you bring up your consuming task, which is in this case the reduce, which then starts consuming your result. Okay, this is basically the kind of operation you know from most of the batch processing systems out there. So this was before not possible in Flink, but now it is possible. Pipeline results, on the other hand, allow you to consume the result while it's being produced. So in this case, after the first part of the result is produced, you can bring up the receiving task and start consuming already. So why would you do this? So as a first result, pipelined intermediate results give you essentially lower latency for your programs. So this is nice. This can mean that your programs finish faster. And blocking results, on the other hand, allow you to reason about your programs in a very nice fashion, because you exactly know when the producing task is online, when it's finished, and you can easily manage your resources. Any questions up to now? Okay. Then I'll continue with the other characteristics. So the next question you might ask about intermediate results is, okay, how long should the system keep these results around? And this is the characteristic, is it ephemeral or is it checkpointed? Ephemeral means nothing else than after a result has been consumed. Let's consume it, we have consumed it now, we can get rid of it. So we don't need it anymore, it's ephemeral. This is discarded. On the other hand, checkpointed results, you produce the result again, consume it, but you keep it around. Okay, what does this give you? For checkpointed results, this allows you to easily do lineage-based fault tolerance, for example. So this is nice to have. What are the benefits? Any questions up to this point? Yes?
One question. At which point would you say does it start to make sense to have this built-in fault tolerance? I mean, how large does your data have to be for it to be necessary to make these checkpoints?
It really depends. What's usually happening is that you, the question was when it makes sense to do these checkpoints. It really depends on your application, I would say, but what's usually happening is, in other systems at least, that you do this after every operator and then get rid of results when you need more memory, for example. But it really depends. If you have an iterative job, it would make sense, for example, to only checkpoint super steps, results at the end of an iteration. Yeah. Maybe Stefan can also.
It depends. I mean, you were asking about data size. There are a lot of computations that are very small data but very expensive, right? So it makes total sense to checkpoint them after the very expensive computation is done. It's, I don't know, It's typically a function of size versus how expensive is it to reproduce it. How much does it cost to keep it around versus how much does it cost to reproduce. This is sort of hard to figure out. I don't think any system does it automatically right now. It's mostly a best effort in terms of how much memory do you have allowed to sort of buffer them versus when do you have to evict them. And, it depends on the application.
Okay, yeah.
So
Felix?
you were introducing the fault tolerance only to the streaming part or also to the batch part? Or
So there's only one part.
Except there's only one part, and this is one part of this one part is the runtime, and what's missing is the scheduling part. Okay. Okay, Thomas?
The blocking checkpointed results, do you
Yeah.
have comparable semantics to the distributed data set from Spark?
I would say yes. Okay, then maybe let's continue and ask questions afterwards. Sorry. Yeah, the benefits of this design is that you really decouple your high-level requirements from the runtime. You don't want your runtime to dictate what you can do. You want a flexible runtime which allows you to really adapt to your use cases. So for example, the way you want to implement fault tolerance might be different for streaming programs than batch programs. Or you want to allow your batch programs to have different optimization paths in the stack than your streaming programs. And this is also what has been done with Flink. Up to now, there have been like heavy data pipelines where it makes sense to split up the long pipelines in batches to make better use of the resources. We also have real-time stream processing jobs running, and with the newly introduced machine learning library and graph library, also like pipelines for these applications. And the current implementations we have in Flink are pipelined ephemeral and blocking checkpointed. And the pipelined results are the default result we use, Flink uses for both batch and streaming programs. And for batch programs, we only fall back to blocking exchange if it's necessary to avoid deadlocks or break up pipelines. So you can find more about this on the wiki. There's a detailed explanation there. And you can also configure this for your programs if you want to via the execution config. You can just call on the environment get config and then set the different execution modes. So the slides will be online, so you can read this up. Yeah. This was it. Feel free to ask questions now. Yeah, Felix.
So I didn't get the last part. Can you actually manually set up that I don't want checkpointing, for example? Does that work?
Yes.
That's cool.
Yeah. Yeah, I think Matthias?
I was wondering, can you mix it basically on an operator basis? You say I want to have like 5 operators in pipelining, and then I want to have a checkpoint, and then I want to have additional 5 operators in pipelining.
Yes.
I think it would be a global configuration.
This is a global configuration at the moment, and this is not. The question was, can you also mix this different exchange modes in one job or in one program? And the answer is yes, but this is not exposed at the moment in the APIs. Yeah. Okay, any further questions?
So a lot of programs will actually mix it automatically for one of the reasons that Ufuk had on one of the previous slides there. If you have a program that you build and it happens to be, let's say, not a tree but a graph that forks and joins back and so on, you can easily run into deadlocks if you do full pipeline processing. So it starts introducing some of these blocking data exchanges there just to make sure that this is at critical spots. So most programs are actually executed as a mixture of pipeline and blocking. And yeah, it would be actually, it might be a nice addition to really expose this to the user that you can say for every point, make this a pipelining one or a blocking point. I would expect that a lot of people will be working around with this. Yeah, definitely for PhD students.
What is doing making these decisions now? The thread?
Yeah, so the batch programs go through this query optimizer, or it's a query optimizer-like component, and that one does an analysis of the flow. So it does a few passes over the program and figures out where certain results are shared in a way that if you consume them pipelined, you run in danger of getting into that long, and then it injects like blocking stages there.
And is there any plan to put the responsibility to the optimizer to decide for pipeline versus fast? I mean, you do it for the cases that you have the dead job, but how about the rest of the cases? Would you do it or not?
I mean, what are other cases? There's definitely going to be the case of breaking up pipelines in terms of reducing memory fragmentation, because if you have a pipeline and all operators are running concurrently, it is in most cases a good idea because you save the materialization of intermediate results. But if all of them sort of consume a good fraction of the memory, there are cases where it makes sense to say, okay, just give more memory to the previous operators and let them fully do their stuff, then break, then give all the memory to the next operators. These cases exist. This is definitely on the plan to push that to the optimizer, but it's not there.
Not only that,
there was some academic work that they were saying, okay, let's figure out where to place checkpoints to balance like dollars and overhead, but I'm not sure how practical it is.
Yeah, if you do it based on some initial statistics, it won't work so well. But now with I saw there was a commit on some statistics collection, so maybe that would give hints for the next iteration, for instance.
Maybe you guys should take this offline. I don't know if this is interesting. Everyone. Yeah.
I have a question. Those checkpointers, if you go for checkpointed logging, so the traditional approach, so to say, how do these intermediate results really look like? You just have them in memory that cannot always be true because memory is limited and data usually...
So we try to keep them in memory as long as possible. If other operators need memory, we spill to disk. And So,
but when they're talking about fault tolerance, there might be that even the job dies completely.
Exactly.
This is something when you say checkpointed and spilled to disk. This is something where you could survive a crash of the job and you resume.
At the moment, no.
Checkpoint.
No.
A crash of the job, yes, not a crash of the hardware.
I understood hardware.
Yeah, no,
as a task manager.
Like the user program, yes, this is what it's really for. If they are not replicated in the sense that that there's a copy of a different machine for this for those at this point. So if for a batch program you physically lose a complete machine, this currently is a restart of the program.
So it's more like if my job crashes, I want to debug, then what I want to do is probably inspect the intermediate results to do this debugging. So the question is, are those intermediate results accessible to me as a...
Not yet.
Kind of fashion?
Not yet, but it's easily possible to implement this. That's a very good point for debuggability.
I'm sure this guy's here. There's someone who's trying to write a thesis on exactly that.
Okay. Maybe.
I'm not sure. Because this whole thing is very, it's exactly very useful for that reason. Assume you have a job that is running and there's a failure that is not due to, let's say, to the system, to hardware, to whatever, but there's just something in your user code and in the data that repeatedly makes your user code fail with some exception. It's something you cannot reproduce locally, but because you have this checkpoint anyways, just grab this data set and this one function and reapply it in a local debugger on this function. So you can sort of put a local breakpoint there and step on the laptop through it. That's the exact idea behind that. It's not there, but it's an idea that has been out, and I think someone's picked it up.
Just for related work, there's a paper, I think, was it BLDB? Semi Salihoglu, one of the guys behind GPS and Giraffe. Had an interactive debugger that would basically sort of work like this, that it would use the parallelism that is sort of understood to exist in these sorts of systems to say, this particular vertex falls over for some reason. Fortunately, we've pickled all of the state associated with it. We remember the messages that you got right before you went down. We can just bring this up on your local computer, and we'll show you what's going on. And I think they've had some experiences with, has this been useful? What do people actually need when they interact with it and try to actually debug the program? But there's a paper to describe what they've done.
I think it's also available in the system scope that Microsoft internally uses to fire the link search. I think they integrated their kernel backend in Visual Studio for exactly that. But they have been bragging about this but not making it available to anybody else.
You don't want to.
Further questions? Or? Yeah.
Just as a follow-up about the data checkpointing. So data checkpointing is done not for the sake of hardware failures, but for application errors. Then how does it actually help? Because if there's an application error that makes the job crash, then in all likelihood the job is going to crash the second time around as well. Because it's sort of deterministic, we would hope. So how do the checkpoints help? If not, we're not talking about hardware failure.
It really depends on the job. So stuff I have seen mostly failure scenarios where like the Hadoop client couldn't like read a block, couldn't read the block, job failed, which is like not this kind of deterministic failure. For deterministic failures, I think you're right at the moment that this wouldn't help that much.
And this is the first step. I mean, a replicated version of this is coming. It's not in there. It made sense for control points. It's much more expensive, but at certain control points you definitely will want that exactly for hardware failures. But I mean, I've been working with these systems for like 5 years. I've never seen a hardware failure on how any of our clusters. I mean, they have them on large clusters, but the case that the HDFS is not responding right now because the name was overloaded or it's just running a garbage collection or so, and the job failing, the job being the source, the sink, I'm sorry, that's writing there, giving up because of that, is something that happens like almost every 10 jobs depending on how you configure your file system or so. And I mean, there's the added benefit that if we manage to overlook a certain bug that causes an undeterministic failure once in a while, it's actually recovered. I mean, let's be honest, there's going to be water to indulge where it's useful that there's some chaos at the end. It's almost impossible to write a failure with distributed systems of photo but yeah, you're absolutely right. The replicated version has to come as well.
And it's also, Robert brought this point up, also useful for like interactive shells where you submit part of your program, produce a like persistent result, and then attach the next part of the program later. Stefan, should we get going with the next talk? Or?
Yeah. Well, maybe
a little break? 5 minutes break?
Let's take 5 minutes break.
Okay.